All right, everybody. In this video, we are going to look at our latest and greatest kind of integrals, and these are the so-called surface integrals. And so just like with our line integrals, we will have two flavors, a scalar surface integral and a vector surface integral. And you can already see the equations for these down below in blue and green, respectively. But first, let's set the stage. So in order to calculate any sort of surface integral, we need a surface that we're looking at. And so this surface, we often denote it with the letter S. It is a two-dimensional surface sitting inside of three-dimensional space. And so, this could look like anything. Maybe it's the surface of a sphere, maybe it's the surface of a cylinder, maybe it's the surface of a graph or what have you. We have some surface that I'm going to call S, and it's sitting inside of three-dimensional space. And what we need to do is we need to parameterize this surface, if we don't already have it, as a parameterized surface, and that's a capital X with parameters U and V. And so as we've already discussed, we can think of this parameterization X as a way to assign each of our three coordinates, so x, y, and z, to be a function of our two parameters, u and v. So we get x of uv, y of uv, and z of uv. And as we've seen, these parameters, so this u comma v, they live within a given domain in what we might call the uv parameter space. And so when I'm denoting this, what I'll often do, let me see, I've used my board space slightly poorly, but I'll drag this over. What I'll often do is draw this kind of schematically. I'll take my UV parameter space. So this is U, this is V, and I have some domain in the UV space. Maybe it's a rectangle or something, but some set of U and V. This is my set D. And then under this parameterization, it will get mapped into three-dimensional space and become S. So we could think of S as being the image of the set D under the mapping given by this capital X. And so that's the role that capital X is playing here. So that is our framework. And I will mention at this point that given our capital X, we have two important vector quantities that we can calculate. And that is the partial derivative of x with respect to u and the partial derivative of x with respect to v. And we're going to give these standard but slightly confusing names. I'm going to call this first vector t sub u and the second vector t sub v. Now we're doing this because these vectors will end up sitting tangent to our surface, but that's unimportant right now. We'll come back and look at that later. Just know that when I take the u derivative and the v derivative, these partial derivatives of x, I'm going to get a vector valued quantity, and I'm just giving them the names t sub u and t sub v. With that in mind, for a given scalar function, little f, and or a vector field, capital F, we get the following definitions for our scalar line integral and our vector line integral, respectively. So the first piece, let's focus on the scalar surface integral first. Our scalar surface integral, this first piece is just notation. And it is saying that we are trying to integrate up the scalar function little f over the surface S. Notice this is a double integral because our S is kind of like a two-dimensional surface. And usually, notationally, when I write my ds, I will make the S here a capital letter S to indicate that it is a surface integral and it's slightly bigger than a line integral. So this is just notation, and I should quickly say the one below will also be notation. But how we calculate these is as follows. For our scalar surface integral, it will be a double integral, but notice we're actually integrating over the domain D. This is a domain in our UV parameter space, which means in the end, we'll end up integrating du dv or dv du. This also means the entire integrand, the entire thing we're integrating, needs to be written in terms of u's and v's. And we do that as follows. We take the composition function little f of x of uv. So we're plugging in our x's, y's, and z's, which are, in turn, expressions involving u and v. And so this is all in terms of u's and v's. And then we are going to multiply it by the following expression. We take tu, cross it with tv, so this is a cross product, get a new vector, and then we calculate the length of that vector. So f of x of uv was a scalar quantity. The length of tu cross tv is a scalar quantity. And then we're just multiplying those scalar quantities together to get a new scalar quantity in terms of u's and v's, which we then integrate du dv. So after we've done that setup and we've computed that integrand in terms of u's and v's, this just becomes a standard double integral integrated over this region in UV space. All right, and that's our scalar surface integral. The vector surface integral is quite similar. It is going to be an expression involving, oh, sorry about that. It is going to be an expression involving the scalar, the vector field, capital F. It is still a double integral over S, and we are integrating ds, but in our usual vector form, notationally, I will often highlight that my f is vectorized, my ds is vectorized, and there is a dot product in play. So that is my evidence. Oh, the dot product disappeared. Let me rewrite that. There it is. This is our evidence that the vector surface integral is, in fact, this vector form. So that is our notation. And the way we calculate this is, again, we're going to calculate our vector composition. This is f of x of uv. And so this gives us a vector valued expression, all in terms of u's and v's. And then we get tu cross tv. And we're not taking the norm of that. We're just taking the vector we get, tu cross tv. So that's also a vectorized quantity. And then we are simply going to dot product it. So we will get this one three-dimensional vector dotted with this other three-dimensional vector. The result is a scalar quantity, as dot products give us. It is a scalar quantity involving u's and v's, which we then integrate du dv over this region D in our UV space. All right, so that, of course, looked a little complicated. Let's at least set up an example down below. So in our example, we're going to let our surface S be the cylinder of radius 1 that goes from z equals 0 to z equals 3. And now we know that this is given by the parameterization. So S becomes this parameterized surface, x of uv equals, and then our quantities are cosine of u, sine of u, and then v. This is our standard parameterization of a cylinder of radius 1. It's because it's 1 cosine u, 1 sine u, and then v. And to line this up correctly, we need u to go from 0 to 2 pi, and v to go from 0, v goes from 0 to 3. So under the kind of schematic that we had drawn before, I might have this as my cylinder, but it's coming from this domain D in my UV space. And specifically, u is going from 0 to 2 pi. So that's my u. And v is going from 0 up to 3. So this would be my region D in my UV parameter space, and that's what's getting mapped to the cylinder surface in 3 space. Okay, great. As part of that process, we need to know, and I'll just calculate it now off here to the side, we need to know TU and we need to know TV. So TU is the partial U derivative of our capital X. So that's going to be the derivative of cosine U, sine U, V with respect to the variable U. And that is just negative sine of U, comma, cosine of U, comma, 0, right? Because the U derivative of V is just 0. We also need TV, and that's the V derivative, so that will just be 0, 0, 1. I'll extend my sidebar here because we also want to compute TU cross TV. That's a piece we'll need to know. And finally, we'll need to know its length as well. So a quick cross product calculation, it's a good chance to dust off those skills. We will get cosine of U in the first position. We will get a negative sine U in the second position. And we'll just get a 0 in the third position. So that is the vector TU cross TV. And then, of course, the length of that vector is going to be the square root of that vector with itself. So that will just be the square root of cosine squared plus sine squared plus 0 squared. And so it's really just going to become 1 in this example. So those are all the major ingredients we need before we even get into calculating our scalar surface integral or our vector surface integral. And now let us at least set up these two integrals. Here I have a scalar function, f of xy, z equals x squared plus y squared. So maybe I'll just highlight or remind you, we are looking at a 3-dimensional scalar function. It just doesn't have any z dependency on it, but it's f of xyz equals x squared plus y squared. Now, if we want to compute the integral over s of f ds, according to our formula above, this will be a double integral over d of the expression f of capital X of uv times the norm of tu cross tv. I'm just pulling the formula from the previous slide. And then that's du dv. But we can quickly compute our region D. This was u going from 0 to 2 pi, and v going from 0 to 3. F of x, this is x squared plus y squared. And so it really becomes cosine of u squared plus sine of u squared. So cos u squared plus sine u squared. And then we are multiplying that by the norm of tu cross tv, which we said was just 1, dv du. And this actually turns out to be pretty straightforward to compute because cosine squared plus sine squared is 1. This will just give us 6 pi as an answer after the dust settles. Now for our vector surface integral, this was a double integral over our surface of our vector field, f dot d capital S. And according to our formula, that's the double integral over d of capital F of x of uv dotted with the expression tu cross tv. And then that's du dv. So again, we can write this out. We know that our d domain is u goes from 0 to 2 pi, and then v goes from 0 to 3. And this will be a dv du in the end when written this way. f of x, well, notice our capital F was x comma y comma 0. And so in this case, we would replace x with a cos u. We'd replace that y with a sine u. And that 0 is just going to be a 0. So we get that expression dotted with, and then tu cross tv, which we saw up above, right? Just sort of looking right here, is also cos u sine u 0 dv du. And so notice when the dust settles, we have this double integral, 0 to 2 pi, 0 to 3. It's going to be cosine times cosine. So cosine squared of u plus sine times sine. So sine squared of u plus 0 times 0 dv du. So once again, we're just going to integrate up the quantity 1 over this region. And once again, amazingly, our answer is 6 pi. Now, of course, these were just some simple examples, but I hope it illustrates the amount of work that goes into calculating either a scalar surface integral or a vector surface integral, including the initial work of parametrizing our surface and calculating the tu cross tv vector. All right, and that's going to do it for this video. Thanks so much for watching. I'll see you next time.